So before we go too much deeper into the study of forces, we want to talk about two specific kinds of forces that are going to come up a fair amount. So the first thing that we want to talk about is the normal force. And I frequently refer to this as the anti-squish force. So surfaces, no matter how they're oriented, surfaces don't like to get squished. And so they will exert a force that, as much as possible, will prevent them from getting squished. So simple example, we have a chair. No, it's not a large H, it's a chair. We have a person sitting in a chair. Okay, they look tiny. So maybe this is a child sitting in a chair. The mass of the child is, say, 40 kilograms. Which means that the weight of the child is, right, mg, so it's going to be 400 newtons of force. Now, the child is in contact with the chair. So if we're looking at the child, right, the weight of the child is pushing down. The child's not actually moving, though. So there must be another force on the child pushing up. Right? And that normal force is it's a consequence of Newton's third law, right? So every action has an equal and opposite reaction. So if the kid is pushing on the chair with 400 newtons of force, then we've got two options. Either the chair breaks or the chair pushes back with 400 newtons of force. More precisely, we might say that this is because, right, the sum of forces in the y direction on this kid are, well, say they're ma, but this acceleration is 0. So the sum of forces on the kid has got to be 0. Right? And there's a force due to the kid's weight, and that's going in the negative y direction. And there's a force due to the chair pushing on the kid. And so in this case, that tells us that the normal force has got to be equal to the weight of the child. Right. This is not always the case. Let's take an example that's oriented a little differently. And this is the famous box on a ramp problem. So we have a ramp, and it's angled at some degree above the horizontal. We'll call it theta, as is tradition. So there's a box up here. The box might be sliding down the ramp. For the moment, let's say that it's stationary on the ramp. So there's enough friction in play to hold it in place, and we're not going to worry about what's causing the friction just yet. That's going to be chapter 6. But we know that friction is a thing that exists, so we're going to say, there is some friction that's keeping it in place. And since the box would tend to move down the ramp, we'll say that the friction has to push up the ramp. There's some other forces involved. There's the mass of this object times gravity, which gives it weight. And because the ramp is not getting squished by our box, at least presumably not, there must be some normal force, right? And normal is a fancy word for perpendicular, right? So the normal force is normal to the surface, that is, it's perpendicular to the surface. So if we take Newton's second law here, right, the box is stationary on the ramp, so the sum of forces is going to be 0. Now, up to this point in the class, we've just been kind of perfunctorily saying that up is the positive y direction, to the right is the positive x direction. That ends here. The simplest way to talk about this problem is actually to say that positive x is up the ramp, positive y is perpendicular to the ramp. The reason for this is when we go to break down our vectors into components, if we had, for example, our usual x and y components, that means that mg would be only in the y direction, but that n would be in the negative x direction and positive y direction, and that f would be positive y, positive x. So we'd have to break down two vectors. But if we just tilt our coordinate system like this, now we only have to break down one, because the friction is all in the positive x direction, the normal force is all in the positive y direction, and the weight is in the negative x and negative y direction. So we have to break down the weight, but we don't have to break down n or f, so we save ourselves some trouble by tilting our coordinate systems. So using this definition of x and y, we can write down our force vectors. So our normal force is nothing in the x direction and something in the y direction. Our frictional force is something in the x direction, nothing in the y direction. And then our weight. That's where things get a little tricky. So we want to think of vectors as the hypotenuse of a right triangle. That's what we've said since day one. So the weight is going straight down. Our x direction goes like this, and our y direction goes like so. So in terms of the x and y coordinates that we've chosen, this is what a triangle breakdown of mg looks like. The last thing, we need to decide where this angle is. So this angle here is theta, which means that the angle up here is 90 minus theta, right? And that's the angle between the weight and the surface of the ramp. Well, if you notice, this angle right here, that's also the angle between the weight and the surface of the ramp. So that must be 90 minus theta, which means that this angle down here is theta. So then in the x direction, the x part of this triangle is actually opposite the angle theta here. So this is going to be mg sine theta in the x direction, and it's going to be mg cosine theta in the y direction. And actually it's going to be negative, right? So the weight is going in the negative x direction, so mg cosine theta, or mg sine theta rather, and it's minus mg cosine theta in the y direction. All right, once we've gotten to here, now we can analyze the forces in the y direction. So in the y direction, we have n minus mg cosine theta, which means that the normal force is less than it was in the case where there's no ramp, where it's flat. So if there was no ramp, we just had a flat floor, then the normal force would just be mg. But if we're tilting it, well, now it's mg cosine theta. So it's less. Because only part of the weight of the box is going into the ramp, and part of it's going down the ramp. And the part of the force that's going down the ramp, well, that's not threatening to squish the ramp at all. So the ramp doesn't need to push back. All right. Do we have any questions about normal force? Everybody seems good on normal force? Okay. Let's talk about one other kind of force while we're here today. We want to talk about tension. So tension is what happens when you try to stretch something. And usually the things we're trying to stretch are ropes. So if we have some rope hanging from the ceiling supporting maybe a pot of geraniums. So we have nice trailing flowers coming out of this flower pot. The flower pot has some weight, but what's supporting it, right? There's no surface beneath it. But what there is a rope hanging from the ceiling. So there must be a tension pulling it up. So that's analyzing the flower pot. If we were to analyze just the rope instead, right, then we would have the rope is being pulled this way by the flower pot, and it's being pulled this way by the ceiling. So right, we expect those forces to cancel out, right, because the rope isn't moving overall. It's just hanging there. So this is one way in which we see tension show up. Right? So ropes, cords, cables, they can be used to take a force caused in one place and move it to another place, right? Because if we're being honest, we know that the force exerted on the ceiling, right, that's going to end up being the same as the flower pot's weight, right? And that's because the rope is being pulled up by the ceiling, which means the ceiling is being pulled down by the rope, right? That's Newton's third law. So we'll switch colors again. The ceiling is being pulled down, okay, by the rope, but it's exerting a normal force to keep itself from being pulled out of alignment. Those end up being canceling to zero because the ceiling's not moving. The rope is experiencing a force from the ceiling and a force from the flower pot. Those end up canceling out because the rope isn't moving, and then the flower pot is experiencing its own weight plus a tension from the rope, and those cancel out because the flower pot isn't moving. There is one very important device that we need to talk about with respect to tension, and that is the pulley. So we have a room full of engineering students here. Someone tell me what a pulley does. Right? It's a rope that lifts an object, makes it easier to lift things, something, reduces force, something. You're all sniffing around the right answer. So actually, a single pulley doesn't make it easier to lift things. What a pulley does is it changes the direction of a force. So it can, if you have a rope going over a pulley, pretend this circle is a pulley, right? You can pull down on one end of the rope and have that downward force be translated into an upward force on the other side of the rope. On the other side of the pulley. So a pulley changes the direction of force without changing the magnitude of the force, at least for this point in the semester. Later, at the very end of the semester, we're going to consider the mass and of pulleys and their friction, but right now we're going to assume that pulleys don't have any friction and they don't have any mass. They only change the direction of forces. So the box on a ramp is one really important kind of what I call toy problem in physics. It's a model for which you can treat a lot of things like boxes on ramps, things like cars going around a banked incline, box on a ramp, suitcase on a luggage carousel, it's box on a ramp, skateboarder getting ready to go down a half pipe, box on a ramp. So lots of different things we're going to treat as a box on a ramp. Another kind of problem that gets used a lot is the Atwood machine. So we have a pulley, a rope, and a box on either end of the rope. So we have the first box has a weight of M1, the second box has a weight of M2, and M1 is bigger than M2. So the question is, at what rate is box 1 falling or box 2 ascending? Well, there are two ways of looking at this problem. One requires a little bit of cleverness, but ends up being really easy to calculate. The other one requires no cleverness. We can just apply our method, bowl through it, and get the right answer. So of course we're going to start with way 2, right? The part that requires no cleverness or insight, but we just apply the method that we've been practicing all semester. And we can start by just doing an analysis of Newton's second law on box 1. So the sum of forces on box 1 equals MA. A is the thing that we don't know, but this is really just a one-dimensional problem. You say up is the positive y direction. So we don't really need to deal with vector force and vector acceleration. It's all just going to be up or down for this problem. So box 1 does have its own weight pulling it down. It also has some tension in the rope pulling it up. So if we add up the forces on box 1, right, tension minus M1G, that equals M1A. Right? So that's what Newton's second law has to say about the first box. Well, what does Newton's second law have to say about the second box? Well, sum of forces on box 2 equals M2A. And box 2 similarly has a tension from the rope that is connecting them. So we have tension minus M2G equals M2A. So you might notice that I have not put subscripts on the T or the A. So the T, right, we have the same rope, right? So a rope can't have two different tensions. And if you have one piece of rope, it's going to be the same tension everywhere, unless you're pinching it or clamping it or something, and we're not doing any of that. Also want to make the note that the tension in a rope, right, is always toward or away from the middle. So the tension that the rope is pulling on the boxes with, right? So over here is, let's say, box 1's side, and it's pulling back to the middle of the rope. Over on box 2's side, it's pulling back toward the middle of the rope. So the rope exerts force toward the center of the rope. That's the first thing that we want to recognize. And that the tension is the same everywhere in the rope. The magnitude, rather, is the same everywhere in the rope. Obviously, if you're on the box 1 side of the rope, the direction of the force will be to the left, and if you're on the box 2 side of the rope, the direction will be to the right. But the magnitude of the tension is going to be the same everywhere. So actually the T's in both of these equations are the same. And then the accelerations I have not subscripted either. And that's because they're connected by a rope, right? There's a fixed length of rope between these two boxes. So at whatever rate box 1 is falling, that's the same rate that box 2 has to be ascending. Okay. So with that said, we actually have two equations and two unknowns we can totally solve. So for equation 1 over here, we're going to write T equals m1a plus m1g. We just solved for T here. And then we can plug that in for T over on box 2. So we have m1a plus m1g minus m2g equals m2a. All right, I'm going to put everything with an a on the right side of the equation, and everything with a g is going to stay on the left side of the equation. So here we have m1g minus m2g equals m2a minus m1a. And on the right-hand side, I'm going to factor out an a here. So we have a, m2 minus m1. And on the left, I'm going to factor out a g, just for aesthetic purposes. m1 minus m2. And then to solve for a, we just have to divide both sides by m2 minus m1. And so we get g times m1 minus m2 divided by m2 minus m1 equals a. There's the acceleration of the boxes. Any questions on this pulley problem? Nice. Yep. As engineers, you should all enjoy a good pulley problem. I would like to note that there is another way of dealing with this problem. Instead of saying that the positive y direction is up, we could have said the positive direction is clockwise. And instead of treating box 1 and box 2 separately, we could treat box 1 and box 2 as part of the same system, right? They're together. They're connected by this rope. So the box, the rope, and the second box, they're all connected in the same system. At which point, we can write down that the sum of forces on the system is equal to MA where the M is the total mass, and the only external forces are m1g minus m2g, where the weight of box 1 is in the positive direction because we said clockwise is positive, and the weight of box 2 is negative because it's in the anti-clockwise direction. Also, I realized I forgot a negative sign and nobody caught it. So on box 1, our analysis over here, box 1's going down, so it has a negative acceleration. Which means we should have a negative sign here, here, positive sign here, here, here. Okay. Okay, so at this point now, in one line, we've written down everything that we did in the original case, right? Sum of forces are just the weights on the boxes. And on the other side is total mass times acceleration. And right away we get so this is kind of a lesson. When you're doing these problems, it is sometimes possible to trade tedium for insight. Not always, but there is always a way to just kind of bull ahead with the method, right? Just apply the tools. So we drew a picture, we applied Newton's second law, and we got an answer. Now, if we had this insight that we could also view this as a kind of rotating thing, like from the pulley's perspective, it simplified things, but we didn't need that insight to solve the problem, right? So the thing I learned from this semester so far is that trying to reason out what exactly is happening is 1,000,000 times harder than doing the math itself. That is 100% correct. So you may have noticed, like on the quizzes, when I'm grading the quizzes, if you just draw out a complete and accurate picture, half points just for that. You draw out a complete and accurate picture and do nothing else, you get 5 out of 10 on that quiz. Because drawing out a complete and accurate picture, that is like most of the challenge. All right. Do we have any other questions before we're done for the day? I know we went a couple minutes longer than we normally do, but I wanted to make sure that we covered the exam, so that there weren't any questions about that when you got your grades back. Okay. So if I don't have anything else for today, this concludes our Monday class. I hope to see you all on Wednesday. So we should be clear on 2 to 5 at this point? Yeah. So at this point, I'm expecting that you have mastered chapters 2 to 5. Yeah. And that you've done however many problems were necessary for that mastery. So for those who are still left, you may have noticed that the problems on the exam seem to have a common source. I didn't try to trick anyone with this exam. They all came straight from the book. And yeah, you should start for chapter 6. I'll mention that in the announcement that I make this afternoon.